Let's look into these examples. So we have several adjustable wrenches here, and we are trying to loosen a stuck nut. Now, assuming that the applied force is the same in each case, the question is, which case results in the largest torque? Now, case 1 and case 3, we have the same size wrench. However, in case 1, this is my force, so this is the line of action of my force. That results in this being the lever arm. In case 3, the line of action of my force is like this. That means my lever arm is this much. If we compare both lever arms, I hope it is obvious that the lever arm in case 1 is larger than the lever arm in case 3. So case 3 is not one of the answers. Now for case 2, we have a larger wrench. The line of action of my force is along this direction, so my lever arm is going to be this much. Since the forces are the same, and here I have a larger lever arm, the torque in case 2 is going to be larger than the torque in case 1, which is larger than the torque in case 3. So case 2 in this case is the winner. Now, of course, we somewhat answered this question in the previous slide. So the question here is asking us about the smallest torque. And obviously, since we have the same force and the one with the smallest lever arm was case 3 results in the smallest torque. Now, this is an interesting question. We have a rod that's lying on a table. It has two equal but opposite forces acting on it. The first question, what is the net force on the rod? Okay. Since these two forces are equal and opposite, the net force should be 0. No question about that. Then the next thing is, will the rod move? Remember, net force is 0. The rod is originally at rest. Newton's first law says an object at rest will remain at rest. An object moving at constant velocity will keep on moving at constant velocity unless we exert on it a non-zero external force, unbalanced external force. We don't have that in this case. So the rod should not move. Now, would the rod rotate? That's a different story. Okay, in this particular case, we don't have a pivot point, so we have to think in terms of the center of mass, which is going to be the center of the rod. F is going to result in a torque that's going to be equal to F times the lever arm. This is the line of action of F. This is the lever arm. The lever arm is the length of the rod over 2. So the torque due to F, the first F, is F times L over 2. And it is in the counterclockwise direction. Now let's consider the torque due to the second force. Let me choose another color. Now the line of action is this way. So this is my lever arm. So the torque due to the second F is going to be F times L over 2. Both of these torques, relative to the center, are going to be able to rotate the rod in the counterclockwise direction. So both torques are in the same direction. They do not oppose each other. They do not cancel each other out. As a consequence of that, we can conclude that the rod is going to rotate. Okay, let's consider this example. A force is applied to a dumbbell for a time interval t. First, as in A, and then as in B. In which case does the dumbbell acquire the greatest center of mass speed? When we consider the center of mass, all what's going to matter is we are applying a force. The force is going to result on an acceleration. F is equal to ma. Both of these cases are identical. Concerning center of mass speed, both of them are going to move linearly with the same acceleration, and they are going to acquire the same speed. And the question is, this is the second question, in which case does the dumbbell acquire the greatest energy? Now, in case A, the force is going to result only on linear motion. The force is not going to result in getting the object to spin.